Thanks for inviting me. I got an email a week ago saying that Oscar wanted to have a second speaker to talk about Bazel, and we don't actually have anyone in the Bay Area. Well, we have one person in the Bay Area who works on Bazel, but not, sort of on the corner things of Bazel, not Bazel. But I'm here this week. I'm actually visiting from Germany, and so they asked me, and I said, okay, I'll do it. And so, as you can imagine, I had a lot of time to prepare these slides, and so this is going to go so smoothly, you won't notice that I didn't practice. All right, so since Oscar already talked about Bazel, I'm now going to talk about machine learning instead. No? All right. So when I started on Bazel 9 years ago, we didn't set out to write a build system that is a functional transformation of your source files. But somehow we arrived there, and we arrived there step by step. So as we were working on it, Google was using this build system, and Google was growing, and we were trying to make it faster and better and more correct. And at some point, a couple of years ago, we said, well, we have 5 different graph libraries in Bazel. This isn't working. Let's start over from scratch. How would we design this if we had to start over? And so we came up with this framework, which I'm going to tell a little bit about today, that actually does implement what Oscar said, a functional transformation of your source files. All right, so what is a build system actually? Well, who doesn't know what a build system is? Excellent, so I can skip this slide. Very good. All right, so what's Bazel specifically? Well, it's a build system, obviously. It's a cross-platform build system. One of the things that Google had to do early was to do cross-platform compilation. Our data centers were all 64 bits, our workstations were all 32 bits, and so we had to cross-compile. And so Bazel naturally evolved cross-compilation support, and I think it's pretty good. It's multi-language. Bazel is used for pretty much all projects at Google, with some major exceptions. Chrome doesn't use it, Android doesn't use it yet. We'll see about that. It's extensible. At the beginning, everything was built into the build system, but that could not possibly scale, right? With tens of thousands of people writing code and wanting to use functional languages, and Fortran, and Lisp. We couldn't put everything into the single build system. So at some point we came to a point where we said, all right, this isn't working. We really have to make this extensible and make it really easily extensible, because everyone is going to want to do that. It's hermetic, sort of. What does hermetic mean, actually? It means that we know what happens in a build. And by knowing what happens in a build, we know if something changes, whether I need to redo the build, and which part of the build I need to redo. And I'm going to talk about that for a couple of slides. It's correct, mostly. I have 2 or 3 changes for the remaining correctness issues that I still haven't quite been able to submit, but we're getting there. And it's pretty scalable. And well, let's start with that. Let's not start with that. Sorry about that. All right, so one of the things that we found was that correctness and performance are not opposed to each other, for the most part. By building a correct build system, we were able to make it faster and faster. And what happens is that when you build stuff, what you really want to do, you want to do as little work as possible. And by having a correct build system, we know exactly what goes on in each step. And that allows us to do as little work as necessary in order to update whatever output files, whatever build you want to do, whatever tests you want to run, whatever binary you want to build. And a key part of that is that we need to make sure that the binaries that we're running on your system, like the compiler and whatever tools you have, that they're correct. But they aren't, unfortunately. If Oscar writes a tool that's just going to go to the disk and read files here and there and everywhere, And so what we're doing is we're sandboxing every action individually so that the action can only read the files that we allow it to read. And that's a critical part of correctness. If we don't do that, it's so easy to get it wrong. So here's a story. When we open sourced Bazel, we didn't have sandboxing. And then one of my colleagues implemented sandboxing about a year later, and he found 20 bugs in our own rules. Because we didn't have sandboxing, we didn't enforce correctness, and so the rules sort of backslid, and we introduced these errors. So at Google, what kind of scale do we have? If you look at Google's repository, most of Google's code is in a single repository. All right. What does that mean? We have tens of thousands of engineers. We have, all right, the numbers don't match up. I'm sorry about that. Those aren't my slides. We have 2 billion lines of code, 9 million source files, and 150 million test cases per day. But just numbers. What's a billion? Nah. All right, let's look at this. This is a couple of software projects. Every dot is 1 million lines of code. So the Linux kernel is 15 million lines. All right. Then OpenOffice is a little bit bigger. Windows Vista. Facebook is a tiny little bit bigger. And almost as big as Debian 5. All right, so how big is Google's source code? Okay? That's the first slide. This is the second slide. 1, 2, all right? And 3. This is Google's source code. It is that large, and Bazel had to work with that. And this is really challenging. Because in this code base, you get every corner case you can imagine, everything, right? We found bugs in the Java 9 compiler where people made changes to the Java compiler and they they fixed bugs, except that our code was relying on the bugs happening. So that's sort of the scale that we're talking about. All right, so I want to talk a little bit about how Bazel works. And now, as I said, we didn't set out to build a functional build system, but we somehow ended up there. And I want to give an example, and I want to walk through that example. I'm not going to give you functional programming code, like Oscar. And Bazel is not actually written in a functional language. It's written in an imperative language, and that mismatch is sometimes causing friction. I admit it. But we make it work. All right, so this is a simple Java file. Anyone could write that. And this is a build file. This is how you tell Bazel what to do. And it's sort of a high-level description of what your intent is. So here you say, I want a Java binary, and it has some Java files in it, and it has a dependency, it has a main class, it has a name, and then Bazel goes ahead and builds that. So what happens here? Now, if you look at this build rule, what it says this build file is a package, and within a package there are rules and there are source files. The source files here the source file is implicit in the glob. Bazel goes and looks at what files are in your directory, right? And then there are some implicit things that are going on where every rule can declare things and can say, I'm going to build a deploy jar. All right. But there is nothing else in this package. There's no magic. We know all these things when we read the package. We know all the dependencies, and there are no other dependencies. There are no hidden dependencies. Everything is explicit in the source file. And so, in terms of terminology, we say this is a rule. This is a Java binary rule. It declares some dependencies. It declares dependency on a bar library. It declares a dependency on a Java source file. And there is one more thing which can happen, which is that the rule can itself also declare dependencies. In this case, the rule says, I depend on a Java compiler. Now, if it was a Scala rule, it would say, I depend on a Scala compiler. If it was a C++ rule, it would say I depend on C++ compiler. But there are no other dependencies. So now when you say, Bazel, please build this, what we do is we build this graph, this dependency graph. And we start with what you want to do. That's a node over there. And then we look at that and say, well, in order to build this, I first have to figure out what's this label? What is it about? What do I want to build? And to do that, it needs to read this package, foo. And that requires reading the build file on disk. And also evaluating this glob to figure out what are the source files that are associated with that. Here I'm using this sort of directory. This is sort of the node that says what are the files in this directory. And so we read the package and everything's good. And then we say, all right, we want to build it. Well, before we can build it, we need to look at its dependencies. So there is a dependency on bar, so we need to read bar. We need to read the build file for bar. We built the package. All right, we got that. Now we want to build it. We want to create the deploy jar. All right, let's do that. In order to do that, we figure out, oh, we have to do 2 compilations. We have to compile bar over there and then main over here. And we have to do it in this order. So there is this edge here which says, I can only compile the main class after I've compiled bar. And then we do that in exactly that order. And we're done. Awesome. All right. Now someone comes and says, oh, but I want to make a change. So makes a change. And then Bazel sees this file was modified. How do we know that? Well, there are several options. We can ask the operating system, which files were modified since the last time. Or we can stat the files and say, well, the stat for this file has changed. It's probably been modified. And then, again, we start at the end. And the first thing we do is we mark all the things that depend on the things that was modified. And then redo the steps. And we're done. And we did the minimum amount of work necessary to update this binary. We didn't recompile bar. We didn't have to. We knew exactly that it wasn't affected. All right, let's say I add a file. Now, this is where this node comes in. This represents the list of files in this directory. So since you added a file, this node was changed. And we recognize that. And then we know that we need to redo that glob. And these are all the things that we need to redo. And again, then when we get to the compile, we see, oh, there is now an additional file. There's also an input to the compile. So we need to declare that dependency. And we have it. All right, so that's pretty cool, I think. Now, how does extensibility work? And when we started to work on this, bless you. When we started to work on this, we were talking about, which language should we use? Well, how should we do this? Should we use a functional programming language? That would be pretty cool because it really matches the model and it would be so powerful. But unfortunately, most of the developers at Google aren't functional developers. They're imperative developers. And so let's stick with an imperative language. Sorry. So we decided to go with Python because the early build files were written in Python. And so we decided to take a subset of Python. It's a proper subset. It's not as powerful as Python, but it's the same syntax. And it's really easy to pick up. You look at it, you can write it almost immediately. It's really easy. It's very familiar. Most people have already written some Python in their life. One of the things that we did intentionally was to leave out all the complicated features of Python. So there is a lot of things you can't do. You can't do monkey patching. Sorry. But for a build system, it's not really necessary. So that's nice. It's also, the way we designed it was we wanted this to be high performance. And Python isn't necessarily known for high performance. So we didn't go with the existing Python interpreter, but we designed our own. And we also designed a thread safety system into this, where we can very heavily parallelize loading packages and analyzing rules, which creates actions which are then executed. There is no global interpreter lock because it's heavily parallelized. It's deterministic. It's deterministic. And you may not realize how difficult it is to get it deterministic. We intentionally chose not to have floating point types in the language, which people have complained about because they want to compute like a percentage in order to do a progress indicator over here. But unfortunately, floating point numbers are not. The standard is really nice, and I recently wrote a paper about floating point numbers, but unfortunately, there are a number of operations that are not fully specified. And so you can't guarantee bit identical results across machines, if nothing else. And so we started writing rules for Bazel, and the community also started to write rules for Bazel. We have Scala rules, we have Rust rules, .NET, TypeScript, and the list goes on. If you want to see the full list, you can go to our GitHub organization, which has a lot of rules, and it's pretty cool. All right, so because it's this functional transformation system, and because we use sandboxing to make sure that actions don't access things that they're not allowed to access, there is magic that comes in, which is for every action, we know what it depends on, we know if actions are independent, and we can ship the action, the entire action, to a different machine. And this is the main thing how we scale to a depot the size of Google, by running hundreds, if not thousands of these in parallel. So if you look at a typical software project at Google, it requires running like 100,000 compilers, compiler invocations, right? 100,000. Even with a fast compiler, this is going to take a while. And the one thing that we do to make this faster is remote execution, distributing this across many machines. And not just distributing the execution, but also caching the execution. If we get a second request that is identical, bit identical to the previous request that we've seen, we return the result from the previous run. And we have gone to great lengths to make sure that you don't get timestamps in your build, and you don't get any other source of non-determinism in your build, so that you get really fast incremental builds and really fast clean builds, really, right? You start at Google, you set up your machine, you do your first build. Most of it is already done because the CI has already done it this morning. There is an open source remote execution service. It's called Build Farm. It's pretty cool. Google also has one that we are looking into making available publicly as a service. Yeah. What's next for Google, for Bazel? We want to really improve our rule story. We want to, not just for Scala, we don't just want to have for Rust, we basically want to have every language under the sun. And in order to do that, we need to support the people who write these rules, and to give them the tools to write really good rules and the data they need to do their job. Android and iOS obviously is a big topic for us. Coverage is still a little bit meh. Coverage is a difficult topic because basically every language invents their own coverage tools and coverage data formats. I hear that Haskell has a coverage format that has a per character coverage information, which is very cool, but okay. What would be really nice, what we'd really like to have would be a single coverage, data format that is cross-language. And the reason why that would be so cool is because you often we have integration tests. We have integration tests that run an iOS app against a Java server talking to another app that is, written in Android, plus a web front end. So we're talking about 5, 6, 7 different languages already. And getting a single unified coverage report would be so powerful. But we're not quite there yet. And of course, we want to do even better on the caching side, on the remote execution side. That code is working, and it's working well. But there are a couple of corner cases. So in practice, many people don't want to check in their tool chains into their repositories, which I completely can't understand. I mean, why wouldn't you want to check in a Scala compiler into your repository? Unfortunately, many people don't want to do that. All right, I understand why you don't want, because it's, it's pretty large dependency. If you look at the, if you look at the JDK, which I'm familiar with, sorry, the JDK is about 150 megabytes. Do you want to have that in the GitHub repository? Probably not. But that means that we lose hermeticity. If you don't do that, we can't guarantee hermetic builds. We don't. Yes, Oscar, please.
Side note, we do actually check in the SHA of the Scala compiler is a jar, so it is actually fully hermetic.
So Oscar says, at Stripe, they check in the SHA of the compiler, so it is actually hermetic. And so we're looking at ways to support that in Bazel itself across the board, even if you don't want to check in the SHA. So for example, I mean, in order to really get hermetic, you have to check in the SHA. But in order to get correct builds, it's enough if we know which files were part of the build. So we can actually track, if you have a local C++ compiler, we can know which files belong to the C++ compiler, and we sort of checksum all of them, and then use that in order to make sure that if you do an incremental build, say after you upgraded your operating system, that you get correct results. That's actually what happened to us at Google. We have people at Google who use Bazel, and we recently had an upgrade to a new version of Debian, and people's builds broke because the compiler is locally installed. So that's something that we want to fix. And then, we'll see who's going to use it. Maybe Angular wants to use it. Docker is pretty big. Maybe we can do better support for Docker, and maybe we can do something more for Scala. Oscar wants us to, I know. We'll see about that. All right, another thing that we're doing is we're actually talking to Microsoft. They have a build system that is sort of similar to Bazel. We're talking to Twitter. They have a build system that's sort of similar to Bazel. We're talking to Facebook. They have a build system that's sort of similar to Bazel. And we were wondering if maybe we could get together and do something together that improves everyone's lives and that allows us to sort of bring this technology to more people in a better way and not have this sort of divergence where everyone uses a slightly different build system and you can't move your code around and you can't use these rules and whatnot. So maybe we will be able to agree to common APIs. We'll see about that. And of course, Bazel is still beta. We're still not at 1.0. We want to get there. A lot of people don't want to use a build system until it has a 1 in the front or some integer number larger than 0. Stripe is happy, so why aren't you? All right. And of course, we want to be more open. We want to make sure that we reply to pull requests in a timely manner, and that yeah, he's been asking about that before the talk. And also that all the changes that we're making to Bazel go through a public review process. All right, if you want to start, try it out. It's Bazel.build. Thank you very much. We have a little bit of time for questions. Anyone other than Oscar? All right, over there. Yes, go for it.
How much progress have you made on that unified coverage format? I just tried to blend coverage across our repositories that didn't work, and it was a pain. There's Komutra, Jacoco, Elcub, and all these other things. Where are you guys going with that? And is there going to be something open source?
The question is, how much progress have we made with the unified coverage format, and is there going to be something open source? Internally, we're doing everything with Elcov. because the C++ compiler is still the biggest part of our, C++ is the biggest part of our code base. I have been looking into open sourcing that, but it's difficult. And LCOF doesn't work for every language, right? So maybe we'll have to ignore the Haskell people. Yes?
More focused on Scala. How much Scala support does Bazel have currently?
How much Scala support does Bazel have currently? Oscar, you want to answer that?
So someone on Christina, I think her name was, made a nice blog post about how to use, how programmable Skylark was. For whatever reason, she chose Scala as an example to make a tooling example. And I saw that about almost 3 years ago and thought that looked kind of interesting. And so me and some other people have started working on that. If you go to bazelbuild.org/rules Scala, we also have a Gitter set up because a lot of the Scala community likes Gitter. Please join and you can see. But we have Scala library, Scala binary, we have GMH benchmark, we have support for specs test, we have support for JUnit test, we have support for Scala tests. We do not have, we have support for TUT if you like your documentation, compile check documentation. We don't have a support for code coverage. We don't have any tooling that can inspect the Scala code and write down the dependencies and I would love to hear more about that. Maybe I'll keep a question. But if you saw the build files that all showed, there's a little bit of duplication between the imports of maybe a Java file and these deps. They're kind of similar, but not exactly the same, and especially probably confusing for new people. So no tooling for that. You've got to kind of write that. But please visit that repo, give it a try. We used it in production for 2.5 years at Stripe. It works very well. We've just deployed caching. Works very reasonably well. Our laptops, because of this hermeticity, laptops are a challenge to integrate with our CI, but it's working very well. We cut our build times of our CI down to from up to 25 minutes. So we have been very basic caching down to something like 3 minutes now. It's working extremely well. So very, very good. So thank you all.
I have one that takes 45 minutes, so I'll look at it. What was the repo, if you don't mind?
Well, Bazel Build /rules Scala. So it's under their org.
Oh, cool.
You'll see the official Scala rules.
Perfect.
They're used by many organizations now. Myself and a gentleman at Wix are the main maintainers.
Okay.
We respond to pull requests very rapidly. Big believers in open source software.
Wonderful, wonderful. I'll take a look. Thank you.
Thanks, Oscar. All right, question over there.
Can you talk a little bit about how often you include a build file? I noticed the recommended is per package. Do people actually do that in Google?
So the question is, how many build files do you have?
Right.
And
Is it per package or less than what's the recommendation?
And the question is, what's the recommendation? How many should you have? My recommendation is 1 per package, 1 per directory, basically. Not everyone follows that, and Google is pretty good at it. But especially if you migrate, say from Maven, where you have a single Maven, POM XML file, many people then end up writing a single build file, and it gets huge. And that's not such a good experience, because then you often end up with a single Java compile, and then it becomes really slow, and we can't parallelize, and so on and so on. But I can tell you what Wix did, the company. They actually, as part of their migration, they wrote really fine-grained build files, and they get super speed up on their builds. So it's really worth it to do fine-grained build files, because you generally get a much better experience. Now, maybe there are languages where it's not a good fit, but I haven't seen one yet. So, all right, Oscar, now you go.
So I'm sure you did see this recent paper by Simon Peyton-Jones and Neil, he worked on Shape previously, and it's this model of modeling Shape and Bazel as Shape is kind of monadic build, whereas Bazel is applicative. And so I'd be interested in your take on that, if you have any comments on it. And secondly, this monadic nature, the lack of the ability to like sequence builds in Bazel hampers us, in particular when we want to bring tools in as repository rules, right? So repository rules, as you may know, they just like, they're binary blobs, you gotta pull them in. It's very difficult to make a hermetic repository rule. So reading that paper, do you think, and I asked you this 6 months ago maybe, has your thoughts changed at all about iterative monadic kind of cycles in Bazel? Or is it like, how do we solve this repository rule problem without some ability to sequence builds in Bazel?
All right, let me summarize that. There has been a recent paper about build systems by a group of 3 people, one of who is at Microsoft. They analyzed a couple of build systems, among which is Bazel. They actually managed to write like a 10-line Haskell description of Bazel, which is very cool. And the question is whether that has changed my thoughts on something that I couldn't quite understand because I have no idea what that is. But I have been in contact with the authors of the paper. There were a few things about the paper where they didn't quite get it right. And I think what you're aiming for is what they call dynamic dependency discovery, which is the idea that you might want to do some work first in order to figure out what work you need to do next. And if you look at Bazel, if you think of the slide I had about how these things fit together with these nodes and these dependencies, that's basically exactly what Bazel does already, except we don't currently expose that to rules. We don't have an API for it. I think we will have an API for it at some point. And I don't think I'm changing my mind here. But I've always thought that this is a really powerful feature that we'd really like to expose. But so far we haven't found a good way to do that. There was a recent proposal on the mailing list from Paul from, I can't remember. Yeah.
For Scala.
For Scala. To do something like, to look at Scala source files in order to figure out what the dependencies are between libraries. And it's a really cool proposal, and we'd really like to do something in that area, and we think it's going to be very powerful and create a bunch of, allow you to do a lot of interesting new things in the build system. Now the question is, do you want to do interesting things in your build system, or do you want to do simple, stupid things in your build system and leave the interesting things to the source code? But I think we're going to offer something in that area. We don't currently have specific plans for that, and it's a little bit tricky because it will break a few invariants that we currently assume. So for example, we do large-scale static analysis over our action graphs to figure out, to generate, for example, IDE information. And if we can't do that anymore, if we have to start running things and reading files in order to generate the information, that potentially makes IDE updates much slower. And we still don't have a good handle on that and how we're going to do that.
So
all right.
Just one follow-up is, maybe it's false, but several of the people at Stripe, some of whom are ex-Googlers, say that in fact the C++ rules take advantage of these features that you're talking about, that you're saying maybe we don't want to allow. And so maybe one of the best things for Bazel would be if all of the rules were in fact implemented the way that you say other people should implement them. Maybe that would advance it more rapidly, because in fact C++ to get good performance also uses this trick, but it's allowed to reach in and break the rules of Skylark and do its own thing. Is that a false, a mischaracterization?
All right. You ask very long questions, Oscar. Let me summarize. Oscar is saying that some of his colleagues at Stripe, who previously were at Google, are saying that we are actually not following the rules ourselves because we have C++ rules that sort of circumvent what we provide in the Skylark APIs and that allow us to do that sort of thing. I have recently been working on open sourcing exactly that part so that people can look at it. It's not all that smart about it, and there are a couple of problems with it that we haven't quite been able to solve yet. But yes, it's sort of doing something like that. We call it include scanning. So when we initially implemented Bazel at Google, we had a previous build system that was called gconfig. And in gconfig, you also had build rules, like here, basically the same syntax. But gconfig was generating a make file. And then the make file would be run through make, and make would run the C++ compiler on your local machine. And the C++ compiler would then go out and look at source files and header files to figure out what files to include. And so C++ developers at Google were used to not having to declare their dependencies in build files. And so as we wrote Bazel, we thought, well, maybe we have to somehow get them into the new system first, and then they will declare the dependencies, pretty please. Unfortunately, they didn't. But instead, it turns out that include scanning is actually it's a performance improvement because it allows us to subset the list of files that we send to the remote machine, right? So we implemented our own C preprocessor that goes through the source files, and it uses our sort of functional incremental execution system to do that so that it's correct. But it reads through the source files to figure out which header files include which header files, and then we get a list of all the header files, and then we send only those to the remote machine. And so for some of the libraries at Google, that's a very significant performance improvement because it reduces the number of files from thousands to a handful. And so it's not quite, fully, I read files and then I declare dependencies based on those, but it's more like a subsetting thing. And so I want to make it open source so that people can look at it and see that we're not doing anything sinister there. And all right, so that's one part of my answer. My answers are also very long. I apologize for that. Second part of my answer is we have just recently started on rewriting the remaining rules in Skylark. So we want no rules to be in Bazel. We want Bazel to be sort of a minimal build system and have all the rules be implemented in Skylark. As I said earlier, Skylark came into being after we had already written a couple of rules sort of built into the build system. And now we have this extension mechanism, and now we want to do everything with this extension mechanism. And there are a couple of reasons why we want to do that. We want to decouple the rules from the core. We want to disallow doing these sort of sinister things with include scanning. Or alternatively, we want to find an API that allows us to do that properly. And that allows other rules to also do that if they want to. Thank you. So that's the second part of my answer, and we're going to work on that over the course of this year, probably next year as well. The C++ rules are incredibly complicated because C++ is so complicated. And we'll have to see how far we get and how quickly we get there. Certainly for some of the simpler rules, like for Python, for example, it's not quite a done deal, but it's going to happen this year. And it's basically straightforward. But for Java and C++, it's going to take longer because those are the rules that we have put the most manpower into to make them fast. And to make them fast, we also introduced quite a bit of complexity, and so migrating them is going to take a while. But there we go. So it's all happening. I promise it's happening. But in terms of timeline, it'll take a while. That's the best I can say. Any questions from someone else? There. Oh, here.
So you mentioned
Yes.
compiler version earlier. What about optimization plans, especially for C++? Do you get requests from developers for custom ones besides what's standard across the board? And how do you give those?
So the question is, I talked about compiler versions, but what about optimization flags and other requests for different optimization flags across a repository?
I'm assuming that there's one standard set of flags for the entire repo.
She is assuming that there is one standard flag for the entire repo. That's not quite accurate. We have a fairly complicated C++ compiler configuration mechanism in Bazel that allows you to do a lot of very interesting and very powerful things. The reason how it came into being is that at Google we have a lot of C++ developers, and we actually have a compiler team. We have a team of people who are working on the compiler, and they wanted to be able to do interesting and novel things with the compiler. And so it's pretty complex. If you are an expert in it, then you can actually write a compiler configuration that allows the users of the repository, the other developers in the repository, to apply optimization flags to subsets of the repository. There is not currently a mechanism for example, to apply certain flags to a subtree, but right now you sort of have to go in and add something to every rule. But you can add it in a generic way, such that if you see, oh, I want to add this additional flag, you do it once in the configuration, and then you don't have to add it, to every rule individually. So, yeah, it's pretty powerful, but it's incredibly complicated, and there are only like 3 people in the world who understand it. There was a question over there. Yes.
Your earlier slide about Google mentioned like 150 million test cases, and I heard you mention testing once or twice, but is this system going to say anything about thinking about testing in some sort of functional way, or is it really just about build artifacts?
So I didn't catch all of that. So you said there was a slide that said we had 150 million test cases at Google, and the question is?
Is this just about creating build artifacts, or is there any other parts of your build process you're thinking about, like testing, thinking about that functionally?
So Bazel has a test command and has a special representation for tests. And we have a fairly complex testing protocol that allows you to do a couple of cool things. Let's see. One of these things is sharding. So since we work very well with parallelism, we can give you a way to take an existing test, which maybe consists of multiple test cases, say in Java, and then to deterministically compute subsets of the set of tests in your target and run them as separate shards, and then we can run all of them in parallel or even on different machines. So that's pretty cool. We have mechanisms to handle flaky tests. So if you have, almost everyone has flaky tests. Who has tests? But we have a mechanism to automatically rerun flaky tests. And that's very, very useful for your pre-submits in particular, which we just recently enabled for our own pre-submits, and it's made our life so much better because now we only get a failure if a test fails 3 times in a row. And 3 reruns are sort of the default behavior, and they are, if let's say you have a test that fails 1 in 100 times, if you rerun it 3 times, it only fails 1 in 100 to the power of 3 times. And that's so much less likely for it to fail. What else do we have? We do have support for coverage. It's not awesome, but it's there. And so we can tell the test, we can build a test with offline instrumentation, or we can tell the test at runtime that it needs to collect coverage, and then it can do runtime instrumentation, and we can collect the data and actually get it back from Bazel. It sort of currently doesn't work in all the cases, but it's there. What else do we have for tests?
Do you do anything to see if the tests are preventing in any way, like try to prevent error?
So we generally encourage people to run their tests in a sandbox. And we actually have for Linux, we have a networking sandbox. So you can say, that my test isn't allowed to access the network, or you can explicitly declare this test is allowed to access the network. You can mark tests as, they are accessing the network, and then Bazel will rerun them on every run, which may or may not be what you want, but yeah, and there are a couple of other cool things about tests that I have forgotten, but look at our testing protocol. It's pretty cool. All right.
Thank you, everybody. I think that's about all.